Hey guys, this video is going to be on backpropagation in feed-forward neural networks, and we're going to be going over the theory and some code examples. So to get the most value from this video, you should be familiar with forward propagation in neural networks, and you should understand the concept of gradient descent. You should also understand what a derivative is and know a bit about vectors and matrices, mainly the matrix multiplication rule, transposition, and notation. You should also understand some concepts from differential calculus, mainly the chain rule and the power rule. We're going to be using these extensively throughout this video. Before we get into the math, let's look at our data to get a better understanding of what we're working with. So, we're going to import NumPy, matplotlib, and a few functions to help us create and split our data. We're going to define n as 1500, or the number of samples that we're working with. We can then create our data using the makeMoons function, which creates a non-linearly separable dataset with two classes. We're going to add in some noise to increase variability. We can split this data using the train-test-split function, and we can define variables for each of our classes. So we'll use Boolean indexing on xtrain to only grab the indices of xtrain where ytrain equals 0. This is going to give us the elements of the first class. We can do the same thing for C2 or the second class. We'll only grab the indices where ytrain equals 1. We can then plot both of these on a matplotlib plot and give them different colors to see the different classes. As you can see, the data takes the shape of two moons when we plot them on a graph. The blue dots correspond to class 1 and the red to class 2. This is what we mean when we say non-linearly separable, because we can't exactly draw a straight line between the data points to separate them. We need a non-linear decision boundary in order to correctly classify class 1 and class 2. Right now, our labels aren't in the correct shape to use in our neural network. They're currently represented by a one-dimensional array for which the element at index I corresponds to the class of the ith sample. What we actually want is a matrix of shape 1502, for which the index of 1 in each column corresponds to the class. We can achieve this by defining an encode categorical function, creating an np.zeros matrix of the same shape as our outputs, and iterating through each sample of y and setting the encoded of index at I to 1 to represent the class. We can return this and then transform both our training and testing data, and then plot the shape of our training data to ensure we did this correctly. Before we can actually code the neural network, we need to lay down some declarations on the architecture. So, we're going to have 2 input neurons, 3 hidden neurons, 2 output neurons, and we're going to be using mean squared error as our loss function. Now we can actually define our neural network class and create the constructor. So, we're going to define a class of nn and create the constructor. This is going to take some input neurons, we're going to set that equal to 2 by default, some hidden neurons, which is 3 by default, and some output neurons, which we're going to set to 2 by default, because we have 2 different classes in our output. The first layer weights is going to be equal to a NumPy random matrix, with the first dimension being the number of input neurons, and the second dimension being the number of output neurons. The biases are going to be another random matrix, with 1 as the first dimension and the number of hidden neurons as the second dimension. The second layer weights is going to be a random matrix with the number of hidden neurons as the first dimension and the number of output neurons as the second dimension. The biases of the second layer are going to be another random matrix with 1 as the first dimension and the number of output neurons as the second dimension. Now, let's lay down some declarations. So, Z of L will represent the unactivated output of the elf layer. So you can think of this as the dot product of the inputs of that layer and its weights. A of L will represent the activated output of the elf layer. So basically Z of L, but passed through the activation function. W of L with the subscripts I and J will represent the weight connecting the ith neuron on the previous layer to the jth neuron on the elf layer. B of L with the subscript J will represent the bias of the jth neuron on the elf layer. And Y with the subscripts I and J will represent the expected output of the jth neuron on the ith sample. So these are going to be our labels for our data. To gain a better understanding, we can give labels to a diagram of a neural network to see exactly where these variables will come into play. So, we can think of these first sets of weights as W1, and Z1 as the dot product of these weights and the inputs of the input layer. And we can think of A1 as both the inputs of the hidden layer and also the activated dot product of Z1. We can think of W2 as the second set of weights connecting the hidden layer to the output layer. We can think of Z2 as the dot product of A1 and these weights. A2 is going to be the value of the output layer, or the activated version of Z2. To gain a better understanding in this video and to better visualize what's actually going on in our neural network, we can represent this neural network as a set of functions that transform a set of inputs x into Z1, A1, Z2, A2, and then our loss matrix. By representing it in this way, we can calculate the derivative of each of these functions with respect to the loss by using the chain rule. This way, we can use these derivatives to adjust the weights and minimize the loss, which is the goal of gradient descent. Now, the shapes of Z1, A1, Z2, and A2 are ambiguous right now, but we're going to explore how they look like in the next few slides. Now let's visualize the data throughout the forward propagation, all the way from x to the loss. So, we're going to start off with a matrix X of shape n and 2. This is because we can expect to have n samples and 2 features in our data that we're using. It's also because we have 2 neurons on the input layer. We will then find the dot product of the inputs and the first layer weights, which are of shape 2 and 3. The 3 columns are from the 3 neurons in the hidden layer. We'll then add a bias of shape 1 and 3 to all of these values in the dot product. This will become Z1, or the dot product of the first layer, which is of shape n and 3. We'll then pass Z1 through the sigmoid function, which will return A1, which is the same shape of Z1 but will become the inputs of the hidden layer. Next, we're going to take A1 and multiply that by the weights of the second layer, which is of shape 3 and 2. The 2 columns come from the 2 neurons on the final layer. We'll then add a bias of shape 1 and 2 to the value of this dot product, and we'll get Z2, which is the dot product of the hidden layer. We'll then pass Z2 to the sigmoid function and get the final output of our neural network, which is A2. A2 is of shape n and 2 because we can expect to have n samples in the labels and 2 features of our labels with the data that we're currently using. Now we can define a sigmoid function that takes in some value x and can calculate the regular sigmoid or the derivative. If we're calculating the derivative, we're going to return sigmoid of x times 1 minus sigmoid of x. If we're just calculating the regular sigmoid, we're going to return 1 over 1 plus e to the negative x, which we can use the np.exp function for. Now we can define the forward propagation function. So we can define a function called forward that takes in some x, and z1 is going to be equal to the dot product of x and the first layer weights plus the first biases. A1 is going to be equal to the activation function, or sigmoid, applied to z1. Z2 is going to be equal to the dot product of A1 and the second layer weights plus the second biases. A2 is going to be equal to the sigmoid function applied to Z2. And we're going to return these 4 values as the output of our function. Now that we've calculated A2, we can plug that into the mean squared error loss function as well as our expected labels to calculate the loss for the forward pass. This can be done using the mean squared error function, which is essentially the difference between the expected outputs and the actual outputs squared. This results in a matrix of shape n by 2 of our losses, and we need to minimize this, but how? In the next slide, we'll be exploring how we can minimize functions and how we can do that with context to the mean squared error function. So, to minimize the mean squared error, we have to think about what it means to minimize a function. So to minimize a function, we have to move the input in the direction opposite of the derivative. This runs the risk of getting stuck in local minimums, but we can mitigate this through different learning rate optimization tools. So, for an example, let f of x equal x squared, and the derivative of f is 2x. The value of f at 5 is 25, and the derivative at 5 is 10. What this tells us is that at f of 5, any small change in the input of f will result in a change proportional to the change in the input of f multiplied by 10 in the output of f. So, to minimize this, we can let a or alpha equal 0.1. This will be our learning rate. Then, we can calculate the derivative at the point that we want to minimize at and subtract the derivative from the input. So, in this case, x can be updated to x minus alpha times the derivative of f at x, which is 4. Therefore, f of the new x is equal to 16, which is less than 25, so we've successfully minimized this function by a small amount. We can apply this to the mean squared error function, but first we need to derive the derivative. So, to find the derivative of the mean squared error loss function, we have to define what the function looks like. So, the mean squared error is defined as 1/2 y minus a2 squared. To find the derivative of this with respect to a2, we can use the chain rule. So, let f of x equal 1/2 x squared, or the outer function. And let g of a2 equal y minus a2, or the inner function. Differentiating f, we get that f prime of x equals x. Differentiating g with respect to a2, we get that g prime is equal to -1. This is because when differentiating g, we can think of y as being a constant and the coefficient of a2 being -1. So differentiating this, we get that the derivative of g with respect to a2 is simply -1. Using the chain rule, we know that the derivative of f of g of a2, or the mean squared error function, is simply equal to f prime of g of a times g prime of a. Therefore, the derivative of the mean squared error function is simply negative y minus a2. Now we can define the mean squared error loss function. We can do this as follows. We can define mean squared error loss and take in some predictions, labels, and a boolean telling us whether or not to take the derivative. If we are taking the derivative, we're simply going to return -1 times the difference between the actual labels and the predictions. Otherwise, we're simply going to return the actual labels minus the predictions squared. So, in order to calculate the derivatives with respect to the weights and the biases, we need to break it down into equations. So, the derivative of the loss with respect to the weights of layer 2 can be broken down into the derivative of loss with respect to A2, the derivative of A2 with respect to Z2, and the derivative of Z2 with respect to the weights of the second layer. The derivative of the loss with respect to the inputs of the second layer can be broken down as follows, with the final term being replaced by the derivative of Z2 with respect to the inputs. The derivative with respect to the biases is simply the sum of the product of the derivative of loss with respect to A2 times the derivative of A2 with respect to Z2. Now, we need to calculate the derivative of A2 with respect to Z2, or the derivative of the outputs with respect to the dot product of the second layer. So, we recall that A2 is simply equal to sigmoid of Z2. So, therefore, in order to calculate the derivative of A2 with respect to Z2, we need to find the derivative of sigmoid with respect to its input. Sigmoid is defined as 1 over 1 plus e to the negative x. Sigmoid prime, or the derivative of sigmoid with respect to its input x, is defined as sigmoid of x times 1 minus sigmoid of x, we're not going to get into the derivation of this formula, but rather just focusing on the application. Therefore, the derivative of a2 with respect to z2 is simply sigmoid prime of z2. Now we need to find the derivative of z2 with respect to the weights of layer 1. So, consider how we derive z2. A1 is the input of the second layer, which is a n by 3 matrix. This is then multiplied by the second layer weights, which is a 3 by 2 matrix, and then added with a bias. And that equals to z2. But how do we calculate the derivative of z2 with respect to w2? Because this isn't just a regular multiplication, but rather a matrix multiplication. Well, we can simplify this into a linear equation just by looking at z2 of 1, 1. This can then be generalized because when we perform matrix multiplication, we're multiplying the rows of the first matrix with the columns of the second matrix. This makes it so that a1 is actually the coefficient of w2 in this linear equation. And by using the power rule, we know that the coefficient of any variable which is not raised to a power is its derivative. So, the derivative of z2 with respect to w2 is simply equal to a1, or the inputs of the hidden layer. Now we're going to find the derivative of the dot product, or z2, with respect to a1. We can do this in the same way we calculated the derivative of z2 with respect to w2, except this time, when we consider the linear equation, we're going to consider the coefficient of a1 to be w2. Notice last time we considered a1 to be the coefficient of w2 because we were calculating the derivative with respect to w2. So, again, using the power rule, we can conclude that the derivative of z2 with respect to a1 is w2, because w2 is the coefficient of a1 in this linear equation. To get a better understanding, we can look at the shape of the derivatives as they're being calculated. So, the derivative of the loss with respect to a2 is simply equal to the derivative of the mean squared error function. This is going to be -1 times y minus a2. This results in a matrix of shape n and 2. We can call this E prime. The derivative of a2 with respect to z2 is equal to the derivative of sigmoid applied to z2. This is equal to a2 prime, a matrix of shape n and 2. Notice how both of these derivatives have the same shape, n and 2. So when we're applying the chain rule, we can simply perform an element-wise multiplication. This is denoted by the circle. When we look at the derivative of z2 with respect to the weights of layer 2, we get a different shape. So recall that the derivative of z2 with respect to w2 is simply a1, or the input of the hidden layer. This matrix has a shape n and 3 and doesn't match the shape of the previous two derivatives. Therefore, in order to multiply this with the previous two derivatives, we have to transpose it, achieving a shape of 3 and n. A transposition essentially means switching around the rows and columns. The dot product is defined between a matrix with shape 3n and n and 2. This is because the inner dimensions must be the same in order for multiplication to be defined between two matrices. So, we transpose the derivative of z2 with respect to w2 as such, and the final derivative of the loss with respect to the second layer weights is the derivative of z2 with respect to w2 transposed times the element-wise multiplication of the derivative of the loss with respect to a2 times the derivative of a2 with respect to z2. Note that the order matters here because matrix multiplication is not commutative. Now we can bring everything together. So, considering the previous equation, we can expand this out and conclude that the derivative of the loss with respect to the second layer weights is equal to a1 dot the element-wise product of a2 prime and e prime. Notice how the dimensions of length n disappeared through this dot product, so it doesn't matter how many samples we have. The resulting matrix is of size 3 and 2, which is the same size as our layer 2 weights. Now we can calculate the derivative with respect to the biases. This is simply going to be the sum of the derivative of the loss with respect to z2. So let's take the element-wise product of a2 prime and e prime and call that a matrix G. The derivative of the loss with respect to the biases is simply going to be the sum of G across the first axis. So you can think of this as adding the rows of G, resulting in a row vector of shape 1 and 2. Writing this in summation notation, we get that the derivative of the loss with respect to the second biases is equal to this expression. So now that we have the derivative of the loss with respect to the biases, we can go about performing the weight update. So let's go over the weight update rule. The difference in the weights is equal to negative alpha, which is a hyperparameter scalar that we pass in, times the derivative of the loss with respect to the weights. And the same goes for the biases. We multiply negative alpha by the derivative of the loss with respect to the biases. What this actually looks like is W2 equals W2 minus alpha times the derivative matrix we calculated in the previous slide. And the same goes for B2. Now we can define a function to perform backpropagation. So we're going to create a function called backprop that takes an x and labels for y, the number of iterations that we're going to do backpropagation for, and a hyperparameter for our learning rate, or we can also call this alpha. Let's set that to 0.1 for now. So we're going to iterate through each iteration, and we're going to grab all the values from the self.forward function. And this is just to measure accuracy, but we're also going to compare the accuracy across each epoch. This is optional for now, but you can implement this if you want to be more verbose. We're first going to copy the weights of the second layer. This is important because we're going to be using them to backpropagate the values to the second layer. So we need an untouched copy of them in order to maintain the correct values. So first we're going to calculate the loss with respect to A2. This can be done by taking the derivative of the mean squared error loss function with respect to A2. So we're going to pass in A2, our actual labels, and we're going to set derivative equal to true. We're also going to calculate the derivative of Z2. This can be done by calling the self.sigmoid function, passing Z2, and setting derivative to true this time. The gradient can be calculated by performing an element-wise multiplication using the np.multiply function. The weight update can be calculated by taking the np ... of the transpose of A1, so that matrix multiplication is defined, and the gradient. The bias update will be calculated by taking the sum along axis 0 of the gradient. This is what we mean by taking the sum of the rows. Now, to perform the weight update, we can set the weights of the second layer equal to -1 times the learning rate times the weight update. And we can repeat the same process for the biases, -1 times the learning rate times the bias update. And now we've successfully updated the weights of the second layer. Now we need to pass on the gradients to the first layer so we can complete one full pass of backpropagation. Moving on to the first layer, we need to define some expressions to represent the derivative of the loss with respect to the first layer weights and biases. So, the derivative of the loss with respect to W1 is equal to the derivative of the loss with respect to A1 times the derivative of A1 with respect to Z1 times the derivative of Z1 with respect to W1. And the derivative of the loss with respect to the input of layer 1, or x, is equal to the derivative of loss with respect to A1 times the derivative of A1 with respect to Z1, and this time we're going to find the derivative of Z1 with respect to the inputs. Now, we won't actually be using this expression because this is for the first layer of the neural network, so there is nothing to optimize. But if we had multiple layers in this neural network, we would pass on this gradient to the previous layer to correct those weights. And the derivative of loss with respect to the biases of layer 1 is simply equal to the sum of the derivative of the loss with respect to Z1, which is represented by this expression. Now, we need to look at the first term of this equation, which is the derivative of the loss with respect to A1. We've actually already defined this on a previous slide with the following expression, and we've actually calculated the first two terms already. Now, for the last term, which is the derivative of Z2 with respect to A1, we need to recall that Z2 is equal to the following expression. So, A1.W2 plus the biases of the second layer is equal to Z2. writing this as a linear equation, we can conclude that the derivative of z2 with respect to a1 is the coefficient of a1 in this equation, which is the second layer weights. So, the derivative of z2 with respect to a1 are the weights of layer 2. Now, writing this out, we determine that we have to transpose this in order for matrix multiplication to be defined if we want to plug it into the equation. So, the derivative of the loss with respect to a1 is the element-wise product of a2 prime and e prime times the transposed weights of the second layer. This is a matrix of shape n and 3, which is the same shape as a1. Now we need to calculate the second term of the equation, which is the derivative of a1 with respect to z1. If we recall that a1 is equal to sigmoid of z1, calculating the derivative becomes trivial. We can use sigmoid prime of z1 and conclude that the derivative of a1 with respect to z1 is simply equal to the sigmoid derivative function applied to z1. Now we need to calculate the derivative of the dot product with respect to the weights of layer 1, or the derivative of z1 with respect to w1. So we recall that z1 is equal to x dot the weights of layer 1 plus the biases of layer 1. And simplifying this into a linear equation, we can conclude that the coefficient of the weights of layer 1 in this linear equation is simply x. So applying the power rule here, we can determine that the derivative of z1 with respect to w1 is simply equal to x. Now we need to find the derivative of the dot product with respect to the inputs of the first layer. Now, we won't actually be using this value because we can't really perform any optimizations on x, since those are our input values. But if we were getting our inputs from another layer, for example, we would be able to perform optimizations on the weights of that layer. So just for intuition, we're going to calculate this video anyway, so you could generalize this to other neural networks. So again, the dot product of x and the layer 1 weights plus the biases is equal to z1. Now, writing this as a linear equation, we can see that the coefficient of x in this equation, meaning what it's being multiplied with, is w1, or the weights of the first layer. So, like last time, using the power rule, the derivative of z2 with respect to the inputs of layer 1, or x, is simply the weights of the first layer. Now we need to calculate the derivative of the loss with respect to the biases. We can do this in two steps. First, we need to look at the derivative of the loss with respect to a1. We've already calculated this as follows. Now we need to look at the expression that represents the derivative of the loss with respect to b1. This is simply the sum over all the rows of the derivative of the loss with respect to a1 times the derivative of a1 with respect to z1. Expanding this out, we already have the derivative of the loss with respect to a1, and the derivative of a1 with respect to z1 is simply the sigmoid derivative applied to z1. This results in a gradient matrix of shape n and 3. We can take the sum over all the rows of G and get that the derivative of the loss with respect to b1 is a row vector of length 3. Now we can calculate the derivative with respect to the layer 1 weights. We recall that the derivative of the loss with respect to w1 is equal to the following expression. We also recall that the derivative of z1 with respect to w1 is simply equal to the inputs of the first layer, or x. Now, expanding this equation out, we once again realize that we have to transpose the inputs of this layer in order for matrix multiplication to be defined. The result of this calculation is a 2 by 3 matrix representing the derivative of the loss with respect to w1. This is the same shape as the weights of the first layer, so we can perform the weight update. Therefore, the derivative of the loss with respect to w1 is equal to the following expression. Now that we've calculated the derivative of the loss with respect to the weights and biases of layer 1, we can go about performing the weight update the same as last time. w1 is equal to w1 minus alpha times the derivative of the loss with respect to w1. b1 is equal to b1 minus alpha times the derivative of the loss with respect to b1. We've now updated the weights and biases of the first layer, successfully completing one backpropagation step. Now we're going to code the update for the weights of the first layer. So we're first going to calculate the derivative with respect to a1. This is simply going to be equal to the dot product of the gradient times the weights of layer 2 transposed. Now we can calculate the derivative of a1 with respect to z1, which is simply the derivative sigmoid function applied on z1. Now we can multiply both of these matrices element-wise using the np.multiply function. Now, calculating the weight update, we can take the dot product of the transposed inputs denoted by the t and the gradient with respect to z1. For the bias update, we can take the sum of the gradient with respect to z1 across the 0th axis. And now, like last time, we can update the weights of the first layer by adding -1 times the learning rate times the weight update, and repeating the same process with the biases and the bias update. We've now successfully completed one backpropagation step in code. Now we can evaluate the accuracy of our neural network. First, we're going to define a predict function that's going to perform the same operations as the forward function, but return a2, or the outputs of our network. Now we're going to create a network object and pass in the necessary parameters. Then we're going to train our network on the training set through 1,000 iterations with a learning rate of 0.01. Then we can grab the predictions of the testing set by using the np.argmax function on the network.predict method and getting the maximum on the first axis, or the columns. We can apply the same thing to the testing set and then compare the two arrays to get the accuracy. We can then print out the accuracy and see how well our model did. Actually running the code now, we can achieve an accuracy through backpropagation of about 86%. This is a lot better than the expected accuracy, which is about 50% for a neural network with completely random weights. This proves that our backpropagation steps worked at increasing the accuracy and minimizing loss for our neural network. Hey guys, the video you just saw was part of my December project to create a convolutional neural network completely from scratch. So I found the most trouble on backpropagation when developing the CNN, so I decided to make a separate video just on backpropagation in regular feed-forward neural networks because that's what I had the most trouble on. And I couldn't find any good resources online that would really go all the way to the low level and explain each step of the process, so I decided to compile all that into one video. So I really hope this helped you develop intuition on how to implement backpropagation in feed-forward neural networks, and I had a lot of fun making this video. If you have any feedback for me, feel free to leave it in the comments, but otherwise, if you sticked around for this long, thanks so much for watching.